Sander, I hope I pronounced that right, are going to talk about IPC. So, a round of applause for IPC in 1, 2, 3.
Yes. So thank you for the introduction. So sorry for the short delay. There was some problem with the connection. Welcome to our talk, IPC in 1, 2, 3. I'm Dimitri. This is Sander. And so we are students, researchers from Ghent University in Belgium. It's not very far from here, from Brussels. And we work on our topic is next generation internet. And if you saw the presentation this morning, we work on European projects, European-funded projects like Irati, Pristine, Arcfire. They are projects in the topic of future internet. And we do research on testbeds which are funded by the European Commission and by the US. FIRE, actually the person that gave the presentation this morning is very involved in this FIRE project, and the NGI is the successor of FIRE. And we also use Genie, which is the global environment for network innovation in the US. And they are very large testbeds that provide us with a lot of servers and interconnections so we can do large-scale experimentation. So why do we need a next-generation internet? Well, if you have been following the news, there's a lot of things that can go wrong. There's attacks on the infrastructure, like on servers, where you do DDoS attacks. Scalability problems, where your BGP routers are overflowing with entries. And there's also attacks on the physical infrastructure from sharks, apparently. They are attracted to undersea cables by the magnetic field, and they disrupt the connections. And also, the Russians are developing ships that could, in theory, break undersea cables. So there's disruptions of the infrastructure. Also, internet security, there's a lot of hacks going on. Bugs and Heartbleed, very important. And also, there are problems with security. We all know the Snowden leaks. And your data is actually worth a lot to a lot of companies, and it's not only the government that's after your data, but also a lot of private companies. They data mine everything. So our methodology is that we basically, we do experimental research, and it's quite hard to do experimental research on the internet of the future because it's not here yet. So we develop it ourselves. So we develop a lot of tools and software, and we then deploy it on our testbeds, and then we write research papers about them. So what we're going to talk about today is about the prototypes that we have been developing, and we are looking at the problems like reliability and privacy on the internet from an architectural perspective. So what you've all been taught in school is like the 7-layer OSI model, and they try to build networks from the perspective that every layer has a different function. They try to split layers by function. But when you look at how it's implemented, that's not always the case. So encryption is in the presentation layer by OSI, but it's implemented in the transport layer with TLS. It's usually also in your application. And there's a lot of technology crossover even in the lower layers. So recent developments for Ethernet, they are actually implementing routing, which is typically layer 3, into layer 2 networks. So there are also technologies like MPLS at layer 2.5, VPNs, which don't really fit the model. IP tunnels don't really fit the model. So a couple of years ago, there's a guy that wrote a book, John Day, and he proposed an alternative architecture for large-scale networks, and it's recursive. So every layer is exactly the same. So we don't say every function is in a different layer, but all layers have all the functions. Possibly, you don't have to implement them if you don't need them. And the only way that the layers are different is by scope. So you have a big network over a small network, and if you need a VPN, you just run it on top. For that to work, you need an identical API between the layers, so you cannot stack them. And currently, that's not the case. So you have the sockets API. You can access every network layer like you want. So if you want to run TCP transport, you would run an internet address family and say, I want a streaming socket, or if you want UDP, you would use a datagram socket. But the API is a little bit different for every layer that you want to use. So what we have been developing is a prototype called Ouroboros. And what is Ouroboros? It's a decentralized packet switch network that is based on IPC. So the API is based on IPC. It's redesigned from the ground up. It follows this recursive model. It blurs the difference between IPC, between local networks, between world area networks. To the application developer, it all looks the same. It looks like IPC. It gives you, we hope, a better service than you are used to from TCP and UDP because we have different ways of implementing this functionality. It's increased privacy, security, anonymity, and it's a very simple API. It's simply the simplest API that I know, and that's where we're going to start. So we're going to look at the Ouroboros API. So you have your computer, you have two processes sitting there, and what happens, your kernel is giving it two process IDs. So we have this layer. We will gradually tell what's in there. So the layering, I think, which one is mine? So, excuse me. So the recursive model always works over a layer. And now it's a very abstract thing, but we'll get to what a layer actually does and what it consists of. So you have a client and a server in your local PC, so it's just one machine, and it gets a PID from the kernel, and we allocate something that's called a flow, and it's an abstract construct. It's a pipe. It's a bidirectional pipe where you write packets on one end, and you have a reasonable probability that you can read them from the other end. So that's a flow abstract construct, and the function of the layer is to provide you with a flow. So the first call is flow accept. You have a server application, it will accept flows. It returns you something that we call a flow descriptor, and any resemblance with the file descriptor is purely coincidental. So on the client side, you have the call flow allocate, which will start a flow towards the server. You could do that based on the PID, but that's a little bit difficult. I mean, that would be every time you start a server, it gets a new PID. So we have a second function that we implement, and it's called binding. So we just assign a certain name in whatever namespace to that process. You register it in the layer. That's a function which we will come back later, and you can allocate to the name. That's roughly the full API. After you allocate it, so it's IPC in 1, 2, 3, these are the three functions. Binding names, registering the name in the layer, and allocating a flow. After that, you can read and write from the buffer. The signature of those calls is exactly the same as read and write from your favorite system calls. And when you're done with communication, you deallocate the flow. So your kernel currently doesn't know these calls, so we had to implement them in our for the system, and we chose to do it in user space. So we have a user space system. We implemented this in C89 just to make it as portable as we could and keep very low dependencies. And it's based on POSIX 2001, 2008, mostly for the threading. We use a lot of B-threads and mutexes, robust mutexes if they're available in the system. It runs on GNU Linux, on FreeBSD, on OS X Sierra, and if you have the Linux subsystem for Windows, it works perfectly fine there. There's some work to get it to run on the GNU Herd, and on Android doesn't completely implement POSIX, so there's more work, and we haven't done that yet, so the prototype doesn't work there. So the core part of the system is a daemon. We call it the IPC Resource Manager daemon, and so you can start this by just running the binary, or you can start it, enable it using systemd so that it actually runs as a daemon in your system. This is a complete source code example. It's C, so if you know C, that helps. If you don't know C, it's reasonably simple and self-explanatory. So you have the full source code of a server and client in C. So the API is extremely simple. You have the server which will accept the flow, a client which allocates the flow to a certain name. We hard-coded that to be echo. The client sends one message to the server sends it back, and they deallocate the flow. So this is the output if you run there. The echo app, it will start the server to say, I get a new flow, and the client allocates it. Client says hi, and that's it. So very simple API, and it's the same API always. So what are the functions of a layer? Because that layer has to provide all the functionality that you need for two processes to communicate with each other. So first of all, the bind operation is not a part of the layer. The bind operation where you bind that process to your name is something that's local to your system, because process IDs you don't need to send that anywhere over any network. So that's a local call in the system. So the only two things that the layer has to produce or to perform is to register names and to perform the flow allocation. So these functions are keep track and figure out where there are endpoints of communication. So that's a directory service. It will map locations on certain names in the network. It will figure out how to get packets from one point to another. So it has to implement routing functionality. It has to effectively forward those packets, so it implements forwarding functionality. And it has to allocate and release the resources, and that's our flow allocation. So this is not an exhaustive list. So actually there are functions in the layer like congestion control, but we're not going to discuss that today. We don't have time. So let's look at local IPC over the Ouroboros subsystem. So usually, if you have a TCP IP stack, local IPC, you use your loopback interface. It goes through the entire stack. So your application delivers it to TCP, to your Ethernet, usually virtualized, goes through the kernel, gets back. So in our system, we can do that as well, but of course it's recursive. There is no really need for all these layers, so you can do it directly over a loopback layer. So we'll show you the actual commands to perform this on your system. So you start the Ouroboros subsystem. Then you start the server, and the first thing that it will do is indicate to the subsystem that there is an Ouroboros-capable server running. This happens all behind the scenes, so you don't have to implement. It's implemented using using the linker, so it's implemented before you even call main. So it just says to that system, I am here, I'm an Ouroboros process. The next thing that we do is bind that name, that process 6417, to the name server. So the Ouroboros system knows that 6417 listens to the name server. Then we create the layer. It's one command. It's a bootstrap command for the layer itself, for all the functionality, for moving packets between the client and the server. Then we register the server into that layer. We don't register the name server directly. We just hash it, so you can choose a hash algorithm as you like. We just hash it it's more secure in the implementation because people cannot start feeding very large strings. And it's more secure as well because if you have to send this over the network, it's less legible and people aren't able to figure out what happens. And then the third step, you start the client. It's a ping client. It will send a number of messages to the server. When you're done, you kill the client, flow gets deallocated, and we're done. So that's how local IPC over the subsystem works. And it's always in 3 steps: binding, registering, and allocating. And that's all that's to it. So there is very little configuration. You don't have to worry about ports or addresses. That's all completely hidden from you. So let's look at Ouroboros over layer X. So we're not on one system anymore. We're on 2 systems. So to run it over layer X, we have to wrap that layer X with our API. So the first thing, we start your Ouroboros subsystem, and we create, in this case, a layer instantiation on that machine, which is attached to your Ethernet device. So the only configuration that we give to the system is, I want something that connects to Ethernet. I give the layer a name, Ethernet, and I say it's connected to my wireless interface. After we do that, I register a name in that layer. So from now, my Ethernet layer, locally, it's something like ARP, but not completely. We implemented it ourselves. So it registers that hash, and it says, on this machine, if I get a request for communication with IOQ3, I'll explain that in short, I will accept it. So instead of only having our own applications, IOQuake is actually an open source project. It's developed from the Quake 3 Arena engine that was a GPL release years ago. and we wrote a patch for it so that you can run the game over our stack instead of over Ethernet or TCP IP. And then I bind the program, this is the binary for the dedicated server. And so the previous time we bound the process, but actually that's also every time you have to look for the process ID. So we just say, whenever this kind of binary is started, just have it listen to IOQ3 names. So we start the server and it's done. So that's the setup of the server side. There is absolutely no configuration involved instead of saying it has to be on that wireless interface. For the client, we start the client. It's the Ouroboros subsystem. Then we say again to the client, we connect it to the wireless interface. And all that client does is start actually the game client. And it says connect, so we modified the game client so that it takes our command. So we say connect it over Ouroboros to the IOQ3 server, and it does it, and you are in the game. So again, it's only 3 commands that you have to give. You register the name, you bind the process to the name, and from the other side, you allocate the name. Pretty simple. So for reliability, Ethernet is not very reliable. So you can have packet loss, you can have jitter, which is normally implemented by TCP IP. And TCP IP is usually in a different layer. In Ouroboros, this is not the case. So it's in the library, and every program that links against our library performs its own connection management. It performs its own encryption and its own checksumming. So when you have the process communicating with each other and something happens to one of these processes, you can recover from a lot of crashes. So only if your actual program crashes, you lose your connection. It does fragmentation, encryption, and checksumming. So we talked about Ouroboros over layer X, so we implemented it over Ethernet. But we actually have a proof of concept that runs it directly over NetFPGA. So it's not over layer 2, it's actually over Ethernet layer 1, the physical. So we're not using MAC addresses or the MAC interface. It's a point-to-point connection over the NetFPGA implementation. We have it over layer 2, so that's the Ethernet that I talked about. And this works on OS X, it works over the Berkeley packet filter. On FreeBSD, it runs over the Berkeley packet filter or NetMap if you have that installed. And on Linux, it uses raw sockets. So the only thing that really does is it takes your packets and flushes it out of the network towards the correct destination. The actual configuration is already happened before. And for layer 3, 4, we implemented it directly over UDP. So for all the functions that a layer has to provide, this flow allocation, routing, forwarding, and directory are implemented in different ways. So for the Raptor NetFPGA, it's all done by us because it's over layer 1. For the Ethernet LLC, it depends on how your Ethernet is configured, but it uses Ethernet. For the directory, it uses Ouroboros. We have implemented it ourselves, but we could use ARP because the ARP specification, it allows you to resolve any layer 3 address to a layer 2 address. But actually, if it's not IP, most switches will just drop it for security reasons. They will check someone is doing something very, very weird on this network. We're not going to allow that. So that's why we're not using the ARP, because it was dropping our packets. And then for UDP, the routing is done, usually use OSPF or ISIS, forwarding IP. And we have implemented a dynamic DNS, which is implementing our directory service. So now we have 2 systems, and Sander is going to show you Ouroboros over Ouroboros. Yeah. You want this?
Okay. Can you hear me?
Yeah, maybe a bit higher.
Is that better? A bit? Yeah. Okay. So Ouroboros over Ouroboros, because it's a recursive architecture. So it's Ouroboros over Ouroboros, over Ouroboros, over Ouroboros, over Ouroboros. So in the previous example that Dimitri explained, we were communicating between two systems. So two applications that are communicating just over the Ethernet layer, so allocating a flow over this Ethernet layer. Of course, we don't want to stop there because we want to extend the scope over which we can communicate. So we wrote a special application called a normal IPC process, which also just uses the same API as a regular application. And one of the main functions of this IPCP is to forward packets that it receives so that we can extend the scope to an internet level in the end. So together, these normal IPCPs, they work together in a normal layer to provide IPC for applications. So you can see that it's basically the same as the applications just over the Ethernet layer, but now it's over the normal layer. So the applications, they don't care what layer they are using. And I depicted the path here, that if the left application would talk to the right application, this is the path through the network that it would follow. So it goes through the normal layer, which uses the services of the Ethernet layer to go to the next IPCP in the normal layer, which then uses the services of the Ethernet layer to reach the final IPCP there until it arrives at the application. Well, I've drawn it like this, but it's important to realize that the normal layer is using also the mechanism of flows in the Ethernet layer, and that no kind of information is exchanged between the different layers. So let's try a bit more difficult of an example. So we can keep on adding layers to extend the scope. So in this example, we have 3 applications, one on system 1, one on system 3, one on system 4, and I've added some layers, and let's say the leftmost application wants to talk to the rightmost application, then the path through the network would be the following. It's also interesting to note that the middle application cannot talk to the left application. It would need another IPCP in the topmost normal layer in order to be able to communicate. It would be able to communicate with the rightmost application by just using the service provided by the second layer, so the first normal layer in its system. So within each normal layer, we have a collection of IPCPs that cooperate with each other to form the layer, and they are all equal. It's completely decentralized, the architecture, so there's no central component, which also makes it more secure and scalable. So the main objective of such a normal layer, I already explained, but this is shown as a top level view of a layer. So the idea is that the IPCP can forward its packets to the destination. So let's say the blue dot represents the endpoints of a flow. And so the idea is that the packet gets forwarded to the destination. So let's think back to how this happens in TCP/IP. So for TCP/IP, you would need to deploy a lot of services, such as the HTTP server for distributing addresses from a central authority. DNS is also not completely decentralized. You would need the different routing protocols, and they're all different pieces of software. You need firewall, stuff like that. So in our system, this is no longer needed. The only thing you need is the IPCP that collaborates with the other IPCPs in the layer to obtain, to provide IPC to its applications. So then how do we construct such a layer? Well, let's go through it step by step. So of course, the first IPCP that you create, it needs to be bootstrapped. So in the example, we have 2 systems that are connected to each other via Ethernet. So we have the Ethernet layer from before again, which here we call E. And on top, we want to create a normal layer, which is called N. So there I've created the first IPCP. So how does this, so when you bootstrap an IPCP, we use, again, the handy tool IRM that we developed. So if you type IRM IPCP bootstrap, it will just output the different things that you can configure. Since it's the first IPCP in the layer, we need to configure it as we please. So for now, it's not super extensive our list yet. But for instance, you can select the routing policy that you want. We implemented link state routing and loop-free alternate, which is a bit more resilient. But for instance, the default is a link state algorithm, and so you can configure it as you please. So depending on the on the environment that it is operating in and the scope that it should have, for instance, the address size. If it's a very large network, you want to pick a much bigger address size. So now let's actually create one. So again, we start the IPC Resource Manager daemon, so the IRMD. And then we simply execute a command which is similar to the one for creating an Ethernet layer, but instead of Ethernet, so first we create, again, the Ethernet IPCP, because we want to use the Ethernet layer for constructing the layer. So we just create the Ethernet IPCP ETH0, as demonstrated a couple of times by now. So as we can see, it has been created in the system. Then next, we instantiate the actual normal IPCP, and here we just selected it with default options. And as you can see, we created into the layer N. We gave the name N1. And we also specified auto-bind, because of course we also need to bind the name so that it's reachable. It needs to be bound and registered, just as any other application. But if you specify auto-bind, it will bind to its unique name, in this case N1, but it will also bind to the layer name N, so that if you want to communicate with the layer, you can communicate with any IPCP that is a member of the layer. So finally, we register these two names into the Ethernet layer so that it's reachable. So enrolling into a layer, this is the next step to extend the layer. So we now have the bootstrapped IPCP, but of course we want to add more IPCPs into the layer. So what this is that a new IPCP that is not yet configured communicates with a member of the layer to authenticate with it, obtain the configuration, and obtain an address in the layer. So in the end, we would end up with this very simple system of one normal layer on top of the Ethernet layer. So continuing on with the example, on the left side, we see again system 1, which we just configured. So we have the Ethernet layer with on top the normal IPCP. And on the right side, we just created an Ethernet IPCP so that we can have communication on top. So finally, you execute IRM IPCP enroll, which enrolls the new member with the existing member. And as you can see, it's a very simple operation. So they just exchange the configuration. It obtains an address as well, as you can see there. And in the end, it is a new member of the layer. Then finally, we also register these names into the Ethernet layer so that it is available if yet another IPCP member would like to join. So once it is a member, the next thing that you want to do is set up data transfer connections, because becoming a member is just that, so that you know how it is configured, but you also want to set up some actual connections to forward data on. So let's assume that we have this data transfer connectivity graph in the layer. Then you can see that every IPCP has an address. Again, we have the endpoints of the flow, and we want to get from the left IPCP to the top right IPCP. So we just send packets in the layer, and as you can see, this is actually the full header. So it's a lot shorter than IP and TCP. We don't send source addresses, so it's a lot more secure and anonymous. The only thing that is needed is sending the destination address so that you know where it is going. But you actually synchronize all the state on flow allocation. So when you allocate flow, you exchange information, and then you generate an endpoint identifier. So that's you also have to send in your packet and a time to live value. So in case you have routing problems, that the packet doesn't loop forever. So it's a very simple header that's maybe 6 bytes, I think, and that's even for a quite big network. So how do you set up data transfer connections? Again, it's with a very simple IRM command. So you connect N1 to N2 for the data transfer component. And when you do that, as you can see, it worked. And it also, because the normal, of course, also has a directory, as Dimitri explained, which is actually DHT in our case. And when you set up the first data transfer connection, it also enrolls into the directory. And then apart from the data transfer network, you can also set up a separate management network within the layer to disseminate routing information, for instance, as we use link state routing, that you can disseminate information about the different links in the network. And it's just, yeah, as you can see, it's a tree, so you can just set the packets down the tree. So the command is very similar to the data transfer connection one. So you just connect N2 to N1. So it doesn't matter because they are all IPCPs are equal. So it doesn't matter if you do it from N2 to N1 or N1 to N2. And here we connect the management component. And as you can see from the output, that both added each other as a new neighbor in the management network. So to summarize here for Ouroboros over Ouroboros, so these are the different functions of the layer for Raptor, the Ethernet and UDP layer. Dimitri explained that one. And so in the case of a normal layer, of course we implement this all ourselves, but the flow allocation is completely Ouroboros. The routing is based on ISIS because you also don't send addresses in ISIS. You just run it directly over your subnetwork technology. The forwarding is also Ouroboros, and the directory is a DHT. Kademlia to be completely correct there. And it does have an enrollment phase. And the legacy technologies, well, almost none of them have an enrollment phase. Wi-Fi has, for instance, that you have to enter your password to connect to the Wi-Fi network. That's a form of enrollment as well, of joining the network. So the reliability, as we said, it's between applications. So since it's a recursive architecture, the IPCPs, they're all just applications as well. So it's one layer that is repeated. But the function of reliability and flow control, checksumming, it can also be repeated. It doesn't have to be repeated, but you can repeat it where it makes sense. For instance, over Ethernet, you probably don't want to do retransmission between those two IPCPs. But if you have a Wi-Fi layer, you can get a lot of packet drops. So it's probably interesting to do retransmission control there. And then in the top layer for the applications, the client and the server, if they want a reliable connection, they should also do retransmission. So we presented the synchronous API, but of course, if you have a lot of flows that you create, you don't want to start a thread for every flow that you create. So we also provide an asynchronous API, which is based actually on KQ. In Linux, you have ePOL. FreeBSD has KQ. They are more performant versions of the select syscall. But when you read the research papers, the KQ one seems to do a bit more, seems to be a better implementation. So it's very simple. So you just, if you create a new flow, then you just add the flow descriptor to the set. And then you can just wait until one of the flow descriptors becomes ready. And then you can read the packets that are stored in the FQ and do what you have to do. So wrapping up.
So I'll briefly summarize what we explained. So we explained a little bit about Ouroboros. So it's our research prototype based on this recursive internet model. It provides you a very single abstraction for ways to communicate between two programs that are running on two machines. It completely abstracts the network. So this simplifies how you write distributed applications. You saw some source code. Of course, it goes. We don't have a lot of time here, so maybe a lot of information to process in a short time. But the idea is that we have a very simple API. We have a very simple command line. So in all the configurations, it's almost a zero configuration network. There is no way that you have to worry about addresses, ports when you are configuring servers. It's a very secure and trustworthy network design, and it hides all the complexity. So if you look at a very abstract way for looking at it, you have a client and a server. We always send encrypted data between a client and a server. Of course, if you don't want to, you don't have to encrypt it, but you can always do that. Everything that you send to the network, like destinations, are registered as hashes. So this is a function like DNS, but there is no encrypted way for DNS. So everything that you look up on the internet, it goes to a DNS server, and it's always unencrypted. So if you're your network operator, if you're surfing for Google, that's encrypted. But then you go to the website, the DNS lookup for the IP address is always unencrypted. The normal layer, it doesn't contain source addresses. So for somebody to try to analyze traffic and figure out where traffic is going, it's a lot harder than current networks. It's completely decentralized. There is no single point in the network that is a central entity. So the way that we do DNS is that it's a DHT that's running everywhere in the network, and the layers are completely self-contained. So there is no information sharing between different layers in the network. So before you start recompiling your kernel without a TCP/IP stack, there's a lot of things to be done. So this is a research prototype. We still have a lot to do, like distributed address assignment. Currently, we just give a random address in 64 bytes. We need to look at efficient layer designs, how to do efficient congestion control. The implementation, we need some bug fixing, optimization. We haven't implemented encryption. So we plan to do that using the GNU crypto library or OpenSSL. And we have to deploy it wider, so we're looking for other people to start trying our stuff and that we can build it at larger and larger scale. So because even the testbeds that we are using, we can go up to hundreds of nodes, but we can't go to thousands or millions, which is eventually where we would like to go. Also, the API is, of course, is proprietary, so your software isn't written for the API. So it's a very simple one. So what we would like to do is have a sockets emulator so that we preload our library before you load the GNU C library, and then we can trap your socket calls and run the software over, so if you want, of course, run it over Ouroboros. So we are on 3 nodes. The channel is Ouroboros. We have a mailing list, and there's the website. So please have a look at it if you think it's interesting what we've been doing in these last 2 years. So we have to acknowledge that it's partly funded by the Flemish government. So if you're not from Flanders, this development has not been wasting your tax money. We would like our colleagues that have already seen the presentation and gave us feedback, because the previous one was probably incomprehensible, even more than this one. So we would like to thank our European and US project partners that were involved in the project that we were in the research, so for all these discussions. Our current and past master thesis students who have been involved in testing the software and deploying it and extending it, and our supervisors for the opportunity that we have to work on this ambitious project. So that's all. Thank you.
Thank you. Now we have 5 minutes, a bit more. We have 8 minutes left for questions. Do I see any? Just a second.
Oh, yeah.
You say that the source address isn't included in the packets, but then how do you do two-way communication?
Just for those who are leaving, please try to do so quietly. Thank you.
So if I got your question correctly, is that we don't send the source address in the packet? Yeah, so when you allocate the flow, that's the first thing you do. So you retrieve the name that you want to allocate a flow to. From the directory, you get the address, and you form a flow allocation request. So this is a packet that does contain the source address. So that's it is sent to the endpoint, which then communicates with the RMD and can see if the flow can get allocated or not. and then a flow allocation response is sent back to the other side. And just with these two messages, they know each other's address and the endpoint identifier that they generated.
So to relate to something that you probably know, if you know TCP, you start with a three-way handshake when you send a SYN AX and ACK. Well, actually, you could do the same in TCP, where you would, at the three-way handshake, you already negotiate the ports and the source address. You store it at the endpoints, and then you never have to send it again. So it's a similar operation, but it doesn't happen in the current networks.
Thanks for the presentation. I'm wondering how the assignment of names on a global scale would work. Like, for example, how would we register FOSDEM.org?
So the question was on registering names on a global scale. So if you want to try to register FOSDEM, well, so this is something that we don't have yet, but you would actually need a naming service that maps the name to the layers that it is available in. So indeed, a global namespace for names would be required. Yeah, probably in the end you might have sort of a public intranet layer to which, yeah, just as we have right now, that you can just then allocate a flow to the name FOSDEM.
Given your answer to the first question, what made you choose flow routing versus packet routing for streams?
So, can you...
Sorry, given your answer to the first question, it seems that you chose flow routing instead of packet routing. Like you establish a flow.
No, the definition of flow is different than in, for instance, MPLS networks. So to repeat the question was why we selected flow routing instead of packet routing. So, but this is, yeah, we are, so the answer is that we are doing packet routing. So the flow is just the synchronization of state in the layer so that you have the endpoints, but from that point on, you're basically doing packet switch networking within each layer.
Okay. Any other questions? Any further ones? I don't see hands. Okay. So, thank you very much for the talk. Warm applause for our speakers. For those of you who are leaving, please look if there's any trash, bottles, or anything that you can take with you and transport outside. That makes everything a bit happier and easier for the rest of us. Thank you.